So if I ask you to take the cube root of the number 8, what you do is you put this radical around it, but instead of not putting anything here and just leaving it blank, you actually put a little 3 right here. So the 3 means we're taking the cube root of 8. Now, how did we do it before? Let's take an easier number, the number 4. When we put a square root around it, we don't put anything here, but there's kind of an implied 2 right here. We didn't write the 2, but the 2, you could write it like this, and this would mean it's a square root. So when you do your factor tree, you say that 2 times 2 is 4, and you're looking for pairs of numbers. Why are you looking for pairs? Because it's a square root, and the number 2 is there. Now, in reality, we don't write the number 2 there. You know that when you see a radical like this and nothing there, you are to assume that it is a square root. So when you build your factor tree, you look for pairs of numbers, and that's how we calculated what the square root is. And the answer to the square root of 4 is equal to 2 because 2 times 2 is equal to 4. All right? So I'll go down here. I'll say because 2 times 2 is equal to 4. Now, what do we do with this? You ask yourself here, since this is a cube root, we're trying to find a number so that when you multiply the number times itself and times itself again, then you get the number under the radical, which is 8. So you ask yourself, okay, can the number 1 be the answer? 1 times 1 times 1 is going to give you 1, and that's not right. But actually, the answer to this is the number 2, right? The cube root of 8 is 2, and the square root of 4 is 2. Why is this the case? Because the answer here, 2 times 2 times 2 is equal to, this is 4 times 2, which is 8, and this matches what is underneath. So you see, when we're finding cube roots, we're trying to find the number that when you multiply 3 of them together like this, you get what's under here. When you're finding square roots, you're trying to find the number so that when you just multiply them with 2 of them here, you get the number. You see the pattern? Square roots, you find something that multiplies twice to give you that. Cube roots, you find 3 things multiplied together to give you the number under there, the same number. Fourth roots, or fifth roots, or sixth roots, or 10th roots would just be the same pattern. A fourth root would be finding a number times itself with 4 of them there, multiplied times itself, to give you the number under there. Now we can still use factor trees for this. I mean, we know the answer because it's so simple, but for the cube root of 8, you ask yourself, well, what is 8 equal to? And you can write down anything at all that comes to your mind. 2 times 4 is 8. Now this one's already prime, we can't break it down any further, but 4 can be written as 2 times 2. And now our tree, we have it down into the lowest form here. We have prime numbers on the bottom. And because we are looking for a cube root here, not a square root, we are looking for triplets of numbers. That's the key difference. And we have a triplet of 2's on the bottom. When you see a triplet, you pull it out, but only if you have 3 of them that you found here, when you find a triplet, it only counts once, and so the number 2 comes out into the answer. Just like for the square root, we were looking for pairs of numbers. What do you think would happen if you were trying to find a 4th root of a number? You would build your factor tree, you would look for copies of 4 of what's on the bottom, 4 copies of some number, and then when you find a quadruple like that, then you would just take it out. It would only count once in that, and then it would go into the answer, right? So square root, you're looking for pairs in the factor tree. Cube root, you're looking for triplets in the factor tree. If you're finding a 4th root, you're looking for 4 copies in the factor tree. 5th root, you're looking for 5 copies in the factor tree, and so on. But like I said, we really don't deal with 4th roots and 5th roots and 6th roots too much in real science and engineering. I'm not saying that they don't exist. I'm not saying that. I'm just saying that it's not as common. Most of the time, we're dealing with square roots and cube roots. So build your factor tree, look for triplets, pull it out, that's the answer, and you can verify that the answer is there because 2 times 2 times 2 is indeed 8. So I do want to talk to you about a little more detail here, but I want to move on to the next couple of problems before we do it. Let's talk about the cube root of the number 1. All right, so let's go ahead and build a factor tree, right? 1 under a factor tree right here. And you ask yourself, well, what times what is 1? Well, 1 times 1 is 1. Now, if this were a square root, you would just stop here and circle these 2 because you have a pair. But I'm looking for triplets, and so I need to keep going. 1 times 1 right here. Now, in the bottom of my factor tree, I have a triplet of 1's. And so the answer to this is 1. And this was a very simple problem because you know that 1 times itself again. 1 times 1 times 1 is 1, and so it is indeed equal to. So for cube roots, you're looking for a number that when you multiply it times itself with 3 of them down there, multiplied times itself 3 times like that, then you arrive back at what you're looking for, the number that gives you, when you multiply it out, what you have under the radical there. All right, let me do one more, and then I'm going to show you how a cube and a cube root are opposite of each other. Let's take a look at the cube root of the number 64. All right, cube root of 64. So let's go over here and do our factor tree. Most people cannot, off the top of their head, just know what number is going to be the answer here. But what you're looking for is a number so that when you take the number times itself again, times itself another time, you get 64. So what we really should do is go off and use a factor tree. Now, what times what is 64? You can use anything you want. I'm going to use 4 times 16, but you could also use 8 times 8 is 64. You'll get the same answer either way. Maybe we'll do it a second time just in a second to show you. You're looking for triplets of numbers. I don't see any triplets here. So there's a couple things you can do. You can go down to 16 here and say, well, this can be written as 4 times 4. And you could stop right there because now I have a triplet, and I have a triplet. I could circle them. I guess I can go and do that, circle them like this. And I have a triplet, and it only counts, the 4 only counts 1 time, and so the answer is 4. And so you know the answer to this is true because, to check yourself, 4, the answer, times itself again. 4 times 4 is 16, and 16 times 4 is 64. And that's the number that gives us what's under here. So the cube root of this is 4. Now, let's do this factor tree a couple of different ways. Instead of this, let's go the other way and say 8 times 8 is 64. Now, I don't have a triplet here. So what I do is I can go and say, well, this is 2 times 4. And this is 2 times 4. I don't see any triplets, so I can just keep on going. The 4 can be broken down as to 2 times 2. This 4 can be broken down into 2 times 2. And now I have prime numbers all at the bottom. And I'm looking for triplets. So here's a triplet of 2's. And here is a triplet of 2's as well. Because don't forget, this one's at the bottom of the tree on this branch as well. And just like in square roots, when you pull them out, this triplet counts as 1 2. And this triplet counts as another 2. And they're multiplied together because all of these numbers on the bottom are multiplied. 2 times 2 times 2 times 2 times 2 times 2 to give me 64. But they just only count 1 out of 3 times, basically. And 2 times 2 is 4, and so you've gotten back the answer that we calculated from here. And notice that we stopped at this point with 4 times 4 times 4 because it was a triplet. You can stop. If we were to continue and break this down into 2 times 2, and this down into 2 times 2, and this down into 2 times 2, we would get exactly what we have down here. 3 2's, and then 3 more 2's, and we would get exactly the same answer. So just like for square roots, when you're finding the cube root of a number, or actually any root, any number root of any number that you want, you just break that factor tree down and you're, in this case, looking for triplets. If you find triplets, you can stop. If you don't, you got to keep going and break it down all the way to the prime numbers, 2, 3, 5, 7, things that you can't break down further. And again, look for those triplets. And then when you find a triplet, you pull it out, but only 1 time counts for every triplet you find. And if you pull multiple things out, they have to be multiplied together. And you can always check your work by doing the multiplication. Now, before we go any farther, I want to stress to you what I kind of taught you in the last lesson. I told you that a square root is like the opposite of a squaring operation. They undo each other. And I told you that in the other way you can think of it, the square operation is the opposite of a square root. And we use these opposites to solve equations. Because to undo addition, we use subtraction. To undo multiplication, we use division. Well, to undo a square root, we square the item. And to undo a square, we can square root an item. And so I was showing you that in the last lesson with the square roots. Now the same thing applies with cube roots. What do you think is going to be the opposite of a cube root? It's going to be the cubing operation, when you cube something. What do you think will be the opposite of the cubing operation? It'll be the cube root. And here's a bonus question. What do you think will be the opposite of a fourth root? It'll be raising something to the 4th power. What do you think will be the opposite or the inverse of the 5th root of something? It would be raising something to the 5th power. Let me show you how this is the case. Let's go back to the previous example where we figured out that the cube root of 8 was equal to 2. What if I actually instead gave you this? 2 to the power of 3 I'm going to wrap that in parentheses, and then I'm going to put a cube root around it. How would you evaluate this? Again, you need to consider this kind of the interior parentheses first and do that first. And so you have to do what's inside here. 2 cubed is 2 times 2 times 2. And so that's equal to 8. 2 times 2 is 4. 4 times 2 is 8. So we do the inside first, but we still have to take that cube root. But we just figured out that the cube root of 8 is equal to 2. So this actually is equal to 2 because 2 times 2 times 2 is 8. So you see what happened is I had the number 2. I cubed it, but then I immediately took the cube root, and the answer I got was just the interior number unchanged. The 2, it's like you cubed it, and then you undid the cubing with the cube root. So these two things kind of cancel each other. That's why I can strike through them, and the 2 is the only thing left behind. That's what I'm saying when one operation can undo another operation. If one thing undoes something else, then you should just have left over what's on the inside. This 2 is the only thing that is surviving the annihilation here of these two things. And we can go the other way. We can say, what if I give you the number 8, and I take the cube root of 8, and then after that, I cube the whole thing? Well, you have to go to the inside, right? What's the cube root of 8? We just found it. It's 2. And we still have to cube it. What is 2 cubed? 2 times 2 times 2. That's 8. So you see what happened is I started with the number 8, I took the cube root, I immediately undid it with the cubing operation, and I get back the exact same number I started with. So it's like the cubing operation cancels with this radical, with the cube root radical, and they undo each other. They basically don't affect what you started with because as soon as you did one, you did the opposite, and so you're left with only the 8. This is extremely useful for solving equations. We want, like if you had an x cubed that you want to solve for x, you want to get rid of the cube on the x variable. So bam, just take a cube root of it. That's going to kill the cube that is on top of your x, which you're trying to get rid of, because you're always trying to get variables when you solve equations by themselves. And if that variable has a cube sitting around it, then you undo it with a cube root. If that variable has a cube root sitting around it, then you undo it by cubing both sides of the equation. You still have to do the same thing to both sides, but you're allowed to take cube roots and cubes and squares and square roots as much as you want, as long as you do it to both sides. All right, so let's do this one real quick, just to show. If I gave you 64, right, and I took the cube root of that, and then after that I cube it, what do you think is going to happen? Well, we just said that the cube root of 64 is equal to 4, and we then have to cube that. And then 4 cubed, that's 4 times 4 is 16. And then 16 times 4 again is 64. And notice that the same number is now left unchanged because the cube cancels with the cube root, leaving behind only the 64. It undoes it, right? And lastly, what about 4 to the third power? And we'll wrap some parentheses around that. And let's put a cube root around that. So what's going to happen here on the inside, 4 cubed, what is it? 4 times 4 is 16. 16 times 4 again is 64. But we still have to cube root it because that's on the outside. We just figured out the cube root of 64 is 4. So the answer is 4. And notice that this number 4 survives unchanged or intact because the cube root and the cubing operation, they undo each other. So we cube and that makes it bigger, and then we cube root it and it makes it smaller, and we get back exactly what we started with. So I want to tell you these things as we learn how to take cubes and cube roots and things like that, because pretty soon we'll solve equations. And I want you to know where we're going with this. A lot of people are like, why do I care about cube roots? It's because we have equations with cubes and with squares, and we want to solve those equations, so we have to do the opposite operation to get rid of whatever we're trying to get rid of that is surrounding our variable. So that's why we use it. That is one of the main reasons why we use it. All right, let's take a look at the next problem. Next problem is the cube root of 27. So let's go over here and let's write our factor tree. So we say, well, what times what is 27? 9 times 3 is 27. And 9 can be written as 3 times 3. Now the 3's are already prime. There's nothing more I can do. So I can stop there and say, well, I'm looking for triplets because this is a cube root. There's a triplet of 3's in the bottom, and they just come out as a single copy of 3, and this is the answer. And this is the answer because, as a check, 3 times 3 times 3 9 times 3, 27, and that is what we have under here. And just to drill home the point that I was talking about a minute ago about how they undo each other, if I take the number 3 and cube it, and then take the cube root of it, what do you think is going to happen without doing any calculations at all? The cubing operation is going to cancel with the cube root operation, just leaving behind what's on the inside, which is 3. Because cubing it is going to give you 27 on the inside, and then taking the cube root of that 27 is going to give you back 3, like this. Last little bit here, if I start with 27, take the cube root of this guy, and then cube it, what's going to happen without really any calculation? You can say, well, this cube is going to cancel with the cube root. They just annihilate each other, and the answer is going to be 27. You don't have to do much, but if you think about it further, the cube root of 27 is 3, and then 3 cubed gives you back 27. So there you go. All right, so that's the last bit I'm going to emphasize on that. I just want you to know that they do undo each other. Let's take a look at the cube root of 125. So we'll go over here and write our factor tree. Cube root 125. So what times what gives you 125? Well, we know that 4 times 25 is 100, so 5 times 25 should be 125. This is already prime, so 25 we can write it as 5 times 5. And everything on the bottom of the tree is prime. This is a cube root, so we're looking for triplets. Here's a triplet that comes out as a single 5, and the answer is 5. We know it's the answer because, as a check, 5 times 5 times 5, this is 25 times 5, 125, and that's it, right? That's it. So you can always check your work. Now here's our very last problem, and this is large enough where I think most people will probably not be able to guess the answer to this question. Let's take a look at the cube root of 216. So we'll go over here and we'll write our factor tree. Now, you know this is an even number because it ends in 6. And so 2 times something has got to be equal to this. And you can do long division to figure out it's 2 times 108, or use a calculator to figure that out if you want. Now, this is also an even number. So you can write this as 2 times 54. 4 times 2, you can convince yourself, is 108. Now this one is also an even number, so you can write this one as 2 times 27, and you can divide that by 2 and convince yourself that this is 2 times 27. Now this one is not divisible by 2, but we know that 9 times 3 is 27, and this 9, we can break it down further to 3 times 3. Now notice we have prime numbers all in the bottom, and we cannot break this factor tree down anymore. But since we're looking for a cube root, we're looking for triplets in the bottom of our tree. Here's a triplet of 2's. And here is a triplet of 3's because this is in the bottom of the tree as well. So this 2 comes out as a single 2, because remember, when you find a triplet like this, it comes out as only one copy. This single 3 comes out and they're multiplied together, and the answer is then 6. The answer is then 6. And you can check yourself on that by checking 6 times 6 times 6. What does that equal to? 6 times 6 is 36. And you could go do 36 times 6. 6 times 6 is 36. 6 times 3 is 18, 19, 20, 21. And you get an answer of 216. So the answer is 6 because 6 times 6 times 6 works out to be exactly what you have under. So I hope now that you can see the parallel and the extreme parallelism between square roots and cube roots. It's literally just looking for more copies under the factor tree. And the reason it works is because you're looking for a number that, in terms of the square root, multiplies by itself, so you only need 2 of them to multiply together to give you for a square root. But for a cube root, you need 3 of them multiplied together. So when you write this factor tree, all the numbers on the bottom are numbers that are multiplied together to give us the number up here. This 216 is 2 times 2 times 2 times 3 times 3 times 3. Everything on the bottom multiplied together. So when I find triplets like that, I'm trying to find triplets because those are the things that when they're multiplied together 3 times is going to give me back what I started with here. So I look for triplets, I pull them out, and anything I pull out gets multiplied together to give us our answer. And you see how we've checked every one of these things. But don't forget the point. The point is we want to solve equations. We have to know how to manipulate these radicals these cube roots, and also we learned square roots. So I'd like you to solve all of these and then follow me on to the next lesson. We'll wrap up our practice with cube roots that involve perfect cubes. By the way, reminds me, these problems are all called perfect cubes because the answer to this question always came out to be a whole number. The answer to this was a whole number. The answer to this was a whole number. They were all constructed to be whole numbers. But if I change the problem very slightly, if I make this 217, the answer will not be 6. It'll be 6 point something. So we're going to get to the place soon where we don't have such simple problems, but we have to use the factor trees to get the answer. So in this case, they're all perfect cubes. In a future lesson, I'll give you questions that do not involve perfect cubes, but you'll see how easy it is once you know how to do it, as we've learned here. So solve these, follow me on to part 2, we'll continue building your skills. Learn anything at mathandscience.com.